Well, here's an interesting example. We have a cone-shaped lamina, or surface S, given by z equals 4 minus 2 times the square root of x squared plus y squared. And here's this picture. Z going from 0 to 4, so the thing stops at z equals 0, the xy plane. So it's just the part that's above that black plane there. Anyway, shown in the picture here, at each point x, y, z on the cone, the density is proportional to the distance between the point and the z-axis. Okay, of course that's the shortest possible distance between the point and the z-axis. Now the question is, find the mass of the lamina. Well, we need a density function, right? And from a point xy on this cone, how far is it to the z-axis? Well, we could pretend the point xy is projected down to the xy plane, and then find the distance from that point xy to the z-axis, and you should see, oh, clearly it's just the square root of x squared plus y squared. So based on the information, the density is proportional to the distance between the point and the z-axis, so therefore we need a constant of proportions k. So that's our density function. Also, we need integration limits from the region in the xy plane that is the shadow of the surface S. So that would be the circle down in the xy plane. And so r could be defined as x squared plus y squared is less than or equal to 4. If you don't see that, let z equals 0 in this cone equation, and then you would see something like that. Actually, you can see it, you know, I have a mistake. That should be less than or equal to 2. So the integral now will look like this. Integral over some region r. They're going to be defined weirdly, but we'll get to it. Here's our distance function, which is the density of the point, and then I didn't say anything about it, but the partial with respect to x of this function would be, well, the 2 and the 1/2 are going to cancel out, and then there might actually be another 2 in there. So something like 2x over the square root of x squared plus y squared, and that, you see, squared would be equal to this, right? And similarly with the partial with respect to y. If you want to see it, go back here and look at it. There's going to be an extra 2 times the 2y that will be in the numerator divided by the square root, actually 2 times the square root of x squared plus y squared in the denominator, but the 2 that's in the denominator, one of these 2's would cancel, but the other one wouldn't. But then we want to square that 2y over, well, negative 2y over x squared plus y squared, so then we wind up with this as our partial derivative with respect to y. And so this integrand algebraically simplifies with some difficulty, but with definitely it's possible. Square root of 5 times k times square root of x squared plus y squared, which would make for a nasty, tough integral, but if we switch to polar coordinates, it's not so bad. And don't forget we have a circle of radius 2, see? So that makes that nice. And by the way, square root of x squared plus y squared is just r. So here's the r d theta, and here's the square root of 5 times our k. R limits going from 0 to 2, theta limits going from 0 to 2 pi. So well, that's 0 to 2. See, I did have a mistake. That when I had that as a 4, that should have been a 2. So, well, this is not tricky integration at all from here on. Integrating r squared over 2, you get r cubed over 3, so we wind up with r going from 0 to 2, so 8 cubed over 3. And then theta going from 0 to 2 pi is probably not too hard for you to see why that comes out as 16 pi times the square root of 5 times k as our result.